Come on in. Morning, everyone. How are we doing? Questions? While we're waiting for everybody to come in. Let's do it. Before we move on, I would like to revisit the fundamental theorem of calculus, because I'm sure some people still have issues. Jennifer is asking for another example of finding the limit of a Riemann sum. We can do that. Do you have one available, or shall I come up with one? And while you're answering that, let's talk about the fundamental theorem of calculus. What does it say? It says that if we define a function as this, if the integrand, you see, the thing is, they're not tough. Once you've understood how everything works, you'll see it's very easy. I was referring to the limits of the Riemann sum business, but I mean, it's true for fundamental theorem of calculus as well, right? So under the assumption that little f here is continuous, fundamental theorem of calculus tells us, Jennifer, that's not an issue, I'll make one up. The fundamental theorem of calculus tells us that big F is continuous, differentiable, and its derivative is little f of x. Let's take an example. Let's take an example of that. I want to go from 0, in fact, just a. Any value a to x, let's change it to 1, of cosine t dt. What the fundamental theorem of calculus tells us is that the derivative is cosine x. Now, I understand that some of you might not really understand completely what's going on, but I think from last time, you now understand how to evaluate this. To evaluate this, you need an antiderivative. So what function has derivative cosine t? You know that very well. You know that to be sine t. The derivative of sine is cosine. So this is sine t between 1 and x. And so this is sine x minus sine 1. And now, right, so observe that this is your original function, big F. Big F is this. So now you can take the derivative, right? The derivative of big F is the derivative of this. Derivative of sine is cosine. Derivative of sine 1, well, sine 1's a constant, so the derivative is 0. And there you have it. But if you take a step back, think about what's really happening. You're finding an antiderivative, and then you're differentiating it. So you're doing something and you're undoing it. You're doing an operation and you're doing its inverse. Paul is asking, big F is continuous on the open interval. It's actually continuous on the closed interval as well. So usually for continuity, we usually ask for closed interval and open interval for differentiability. What is the difference between the result of f prime equals cos x and 0? I don't know what 0 you're referring to. And Bahar is asking, why do we do something and then undo it? Well, that's the whole point, right? You don't need to do something and undo it. That's what the fundamental theorem of calculus tells us. You don't need to find an antiderivative and then differentiate. You can just right away give the answer. And if we take this a step further and look at something like this, which is what we were doing last time, what is the difference between f prime equals cos x and sine x minus sine 1? Well, sine x minus sine 1 isn't f prime. It's the original f. Nolan is asking, when the integral limits aren't variables, but instead two values, how is it that we can solve for the derivative and then the antiderivative? No, that's the thing. If the integral is the integral from one value to another, then this represents the area underneath the graph. It's a real number. Nobody's taken the derivative of that. Because if you take the derivative, of course, it's going to be 0. If the antiderivative of big F is the area underneath the graph, what does its derivative represent? You know exactly what its derivative represents. The derivative represents the rate of change. So by how much does big F change? Little f of x. Which is also the slope of the tangent line of this function. Right? And let's discuss this by the fundamental theorem of calculus with the chain rule thrown in, right? What is this? How do we differentiate this business? We plug in the top limit and then differentiate what you plugged in. Subtract, doing the same thing for the bottom limit. Now again, you might not be totally comfortable with that. Why do we differentiate what we plugged in? What's going on here? Well, again, this is an easy example where you can find an antiderivative. What is the antiderivative of cos? Again, it's sine between x squared and root x. So this is sine root x minus sine squared, sine of x squared. Right? This is your original function. So you know how to take the derivative of that. The derivative of sine is cos. So cos of that times the derivative of the inside, right? Chain rule. Minus derivative of sine is cos times the derivative of the inside. It's beautiful how everything comes together, right? are we doing? Somebody wanted an example of a Riemann sum business. Let's do this one. So if he is asking the derivative of the integral should be what we started out with, well, I mean, look, fundamental theorem of calculus tells you the derivative of this is that. What is the difference between sigma and the integral sign? Oh, you know the difference. Sigma is the sign, exactly that. So what is this limit? What is this limit? I claim that this limit is actually equal to here's my claim. This limit is equal to the integral from 0 to 1 of cos x dx. And this is, of course, antiderivative of cos is sine from 0 to 1, which is sine 1. So that limit is sine 1. We've evaluated that limit to be sine 1. How did we come up with that? What's the idea? The idea is that you have to realize this thing here as a Riemann sum. You have to realize that as a Riemann sum. A Riemann sum for some function on some interval using some partition. So we wish to realize that as a Riemann sum of some function using some interval and some partition. Well, you're looking at cosine of I over n, where I goes from 1 to n. So cosine of 1 over n, cosine 2 over n, cosine 3 over n, all the way to cosine n over n. We've seen that before, right? This is the partition. If you partition the interval 0, 1 into n pieces, That's exactly what the right endpoint of each subinterval is. And if you throw in a cosine function, then cosine 1 over n, cosine 2 over n, and so on is going to be the height of each rectangle. And each rectangle has width 1 over n because it's a regular partition. So this thing right here is the Riemann sum of cos x on the interval 0, 1 using a regular partition and the right endpoints. The right endpoints of each subinterval. Not easy to see the first time you're doing this, but with practice, right? So this is, if we look at that again, this is cosine 1 over n times 1 over n, right? The over n business here. Plus cosine 2 over n times 1 over n. And so on all the way to cosine n over n times 1 over n. So that's exactly what you get with this. Why is it from 0 to 1? Because it works. It works. But here's the beauty, right? Because you have three things to come up with: function, interval, and partition. And which endpoints or which points you're actually using. So really 4 things. I proved a few years ago that you can assume it's the interval 0, 1. You can always assume it's the interval 0, 1. And we will prove this together Tuesday. You can always assume it's the interval 0, 1. We'll prove it on Tuesday. It's not immediately clear. It's not immediately clear that you can always take 0, 1. We'll prove it on Tuesday. You can assume for any Riemann sum. It can be 1 to 2 as well, absolutely. But you can always assume 0, 0, 1. Coming back to, because somebody was asking the difference between the integral and the sum and the sigma. Let me point out the beautiful notation, right? I mean, we have this, or in general, what does a Riemann sum look like? Right, you have some function evaluated at some points, left-hand points, right-hand points, midpoint, or anything else. And then you're multiplying by the width of each subinterval. If you can take the subintervals to be a regular partition, that's fine, but it doesn't need to be, right? So let's say the width of each subinterval is delta xi. Right, so that's what a Riemann sum looks like. That's what a Riemann sum looks like. And if your function is Riemann integrable, such as cosine x, because you know cosine is continuous, so it's a Riemann integrable function. If your function is Riemann integrable, then this limit is actually the area underneath the graph. So this limit is the area underneath the graph. And let me bring your attention to the beautiful notation, right? The sigma notation becomes an integral. An integral, an elongated s for sum, right? There's a big S here. So the sigma, the sum, becomes an elongated s, becomes an s. You've got your function, and the delta x becomes a dx. The tutorials will be recorded. One of them will be recorded for those in a different time zone. So these will be posted Friday afternoon. You should make all attempts to go to a live tutorial. But if you cannot, and if you cannot make the tutorial you're registered for, please go to any other tutorial. It doesn't matter. But please try to attend a live tutorial. Tutorials are not mandatory. No. I mean, look, all of these, you know where your marks are coming from, right? Web work, midterm final. All right. Questions here? How are we doing? The dx, for now, as far as we're concerned, dx is just notation. It's what is happening to this width as you're getting smaller and smaller. Right? These widths are getting smaller and smaller. Going to 0, that's your dx. All right, before we move on, let me go back . Yeah, the long S is just an integral sign, right? I'm suggesting why this Leibniz notation, right? We had a sigma, it becomes an integral along S. Recall in Cal 1, if S of t is the position of a particle, the derivative was the velocity. And the derivative of the velocity was the acceleration, right? How fast the position changes, or the rate of change of the position is the velocity, how fast you're going, and the rate of change of the velocity is the acceleration. Here, if we're talking about antiderivatives, the antiderivative is going to be the velocity. The antiderivative of the velocity is the position, more or less, right, to within a constant. In particular, If you have a definite integral, right, you know a function, you know an antiderivative of v, that's just s. So that's s of v minus s of a. The difference in position, also known as the displacement. Right? If I put a dot on the board here and everybody leaves the room and you come back and the dot is now here, well, this is the displacement. The dot has moved from here to there. That's how much it was displaced. Now, it might not have moved in a straight line, right? It might have moved here and then come back or gone elsewhere to this, but you wouldn't know. All you can measure is the displacement. If it went elsewhere and so on, it might have traveled more than just this, which leads us to the idea of distance traveled. The distance traveled is the integral of the absolute value. There it is. Let's take a few examples. This is taken from we are given the acceleration, velocity at 0 as -4. Find the velocity and distance traveled. All right. So we have the acceleration given. Let's find the velocity by taking the antiderivative. That doesn't necessarily give us the velocity, but go within a constant, right? Because you know the plus c. So acceleration 2t plus 3, what function has derivative 2t? You know that to be t squared. What function has derivative 3? That's 3t. Right, so you know this is correct, because if you take the derivative of t squared is 2t, derivative of 3t is 3, derivative of c is 0, and we're done. So That's your velocity to within a constant. But you know v of 0 is -4. So if you plug 0 into this, what do we get? We get c. So c has to be -4. Well, I mean, here, the c is very important, right? If you didn't have c, you'd get the question wrong. So we conclude that the velocity is t squared plus 3t minus 4. And what do we want? We want the distance traveled. The distance traveled is the integral of the velocity between 0 and 3, of the absolute value of the velocity. Why absolute? The idea is that, right, I mean, as I was suggesting, if you have a particle and you're moving and you're coming back, this is the displacement, right? This is going to be the displacement, but the distance traveled, you actually went all the way to here and then you came back to there. So you want to add all of those distances up, you know, I mean, think of being in a car, moving forward and going reverse. You want to add all the distance you went forward and the distance you went in reverse. Reverse meaning negative. You don't want to add a negative number, but add its positive counterpart. And the absolute value takes care of that. But we must now get rid of the absolute value in order to find an antiderivative. Let's look at this function, t squared plus 3t minus 4, which factors nicely, does it, as t plus 4, t minus 1, it's actually v. So let's draw a chart for v. Draw a chart for v. V is 0 at -4 and +1. And in between, so first of all, if you take large negative values, this is going to be negative, this is going to be negative, so the product is positive. If you plug in 0, this is negative. And if you take something like 5 or anything bigger than 1, if you plug in 2, this is positive, so the product is positive as well. So this tells us where v is positive and where v is negative. Right, since we're restricting our attention to the interval 0, 3, you see what's going to happen, right? Between 0 and 1, the function is negative, and between 1 and 3, the function is positive. So the distance traveled, which is the integral of the absolute value, we can break this up naturally as the integral from 0 to 1. Plus the integral from 1 to 3. All right. So you see, by doing this, in the interval 0 to 1, this function is negative. So the absolute value of that function is negative of that function. And in the interval 1 to 3, the absolute value of that function is just that function. How are we doing here? So now these are just powers of t. You can integrate easily. Antiderivative of t squared, 1/3 t cubed. Antiderivative of 3t minus 3 over 2t squared. And 4t between 0 and 1 plus 1/3 t cubed. 3 over 2t squared minus 4t between 1 and 3. Mahar is still confused as to why v of 0 is -4. That was given in the question. Fardeen is asking if we can just put an absolute value outside. The answer is no. Completely different. Well, I mean, after you've split it up, it would actually be fine, but let's not do that. Amir is asking why 4t between 0 and 1. I don't know what you're talking about. This thing here? I mean, it's not just the 4t, it's the whole thing, right? You cannot just simply integrate it. No. We're not looking for displacement. We're looking for distance traveled. Yeah, so it's not just that, it's the whole thing. Right? So when t is 1, subtract when t is 0, but when t is 0, all the terms are 0. And then when t is 3, we get 9 plus 27 over 2. minus 12, and then subtract when t is 1. There it is. So what is that? Minus 2/3. This is minus 3 over 2, so minus 6 over 2, that's minus 3. Minus 3 plus 4 is 1, plus 9 is 10. It's minus 2, so there's going to be a plus 2. And finally, we have the 27 over 2. And I put all of that over 6. What do we have? 6, 7, 81. 81 plus 12. So 93 minus 4. 89, is that correct? 89 over 6? Anybody? Selena is unsure why we're using negative if it's absolute value. In the interval 0 to 1, your function is negative. So the absolute value of the function is negative of itself, right? If you remember from calculus 1, we had this very nice piecewise defined function for absolute value of x. Absolute value of x, if x is bigger than 0, absolute value of x is just itself. And if x is less than 0, absolute value of x is negative x. This is what I'm using here. And we'll be using that over and over and over again in this course. Right? Let's convince ourselves once again, if you have forgotten this. Absolute value of 2, you know it's just 2. Absolute value of 3, of negative 3, you know it's 3, but we can rewrite it as negative 3. So this is your x here. It is negative of itself. That's what we're using. R is asking if C is always the initial quantity. No. It really depends on your function. 89 over 6 is correct. Thank you, Andrea. Why is there no constant term in the formula, right? Why not a plus C? An excellent question. We saw last time that since these are definite integrals, you don't need an arbitrary constant. It's just going to cancel itself out. Right? Suppose you had a plus 6 here at the end. So you'd get a blah, blah, blah plus 6. And then when you plug in the 0, you would get a minus 6 and they would just cancel anyways. No need for an arbitrary constant here. All right, how are we doing here? Questions? Let's move on to the real material for the day. Where we will consider something like this. What is the antiderivative of cosine 2x? I'm sure you can fiddle your way through this, right? You know that the derivative of sine is cos, so you might start with a guess of sine of 2x, but when you differentiate this, derivative of sine is cos, you get cos of 2x, but then you know you have to differentiate the inside, and you get a 2. You get an extra 2 that you didn't want, so you might try to compensate by multiplying by 1/2, and you've got the right answer. Absolutely. However, the question arises, is there a systematic way to treat this without any guesswork? Indeed, there is. If you didn't have a 2 here, the integral would be very easy. Right? If there's no 2, the integral is very easy. So let's make a substitution. Let's call this 2x u, so that this becomes cosine of u. The only question that arises, what about this dx? Well, du, I mean, if u is 2x, then what's the derivative of that? The derivative, du dx, is just 2. Now, in a terrible abuse of notation, imagine bringing this dx to the other side. So that du is 2 dx, even though that is completely illegal, it actually does give us the right answer. Bring the 2 over, so 1/2 du is dx, and now we're ready to substitute everything. The dx is 1/2 du. Cosine of 2x becomes cosine of u. And there we have it. So 1/2 is just a constant, we'll pull it out. Antiderivative of cos u, what function has cos u as its derivative? You know that to be sine u. Throw in an arbitrary constant. Replace, u is 2x. And we're done. Exactly the answer we had originally guessed. This process is known as a U-substitution. This process is known as a U-substitution. Where does the 1/2 come from? It comes from the dx, right? Du dx is 2, so du is 2 dx. Bring the 2 over, 1/2 du is dx. So this dx is 1/2 du. So this process is known as a U-substitution, and as you can see, right, it's really the chain rule in reverse. So it's really the inverse operation of the chain rule. The 1/2 does not get multiplied into the function, right? It's just outside. Well, the U substitution is the opposite of the chain rule. Let's take a few examples. As suggested, this U-substitution can be used for far more complex functions. Consider this example. And again, let me point out that there isn't necessarily a unique way to do these questions. There may be more than one. There may be more than one U-substitution that you could do. Your thoughts here? Where did du dx come from? Well, I mean, look, you have u as 2x, du dx is just the derivative. I'm asking, what is the derivative? If u is 2x, what is the derivative of u? You know it to be 2. So I'm suggesting, or I'm asking for a u substitution. What are we going to take for u? I think Matthew is suggesting negative x squared. Seems reasonable. Let's see what happens. Again, there are several options. Amir, I'm sorry, what are you asking here? How did you write that second line? This one here? What are we? This one? So many second lines. Let's go with u is negative x squared, so that the derivative, du dx, how do you know what to choose for u? Well, that's the thing, right? I mean, that's an obvious question that arises. And the answer to that is experience. You will do so many of these questions that you're just going to see it immediately. If u is negative x squared, du dx is negative 2x. That comes as no surprise. Absolutely. And notice, if you look at your integrand, you have the x dx right here. Right? So again, in a terrible abusive notation, du is minus 2x dx. And the x dx is exactly what you have here. So let's bring this minus 2 to the other side. It becomes minus 1/2. And so this x dx is minus 1/2 du. And then we're just left with the exponential, which is e to the u. Right? It's e to the negative x squared. It's e to the u. There it is. Take the negative 1/2 out. What function has derivative e to the u? You know that. Well, somebody's asking where the 1/2 came from here. It comes from the same place as this negative 1/2. It comes from this work right here. Right, thank you. E to the u plus an arbitrary constant. And plug back in. negative 1/2 e to the negative x squared plus c. Let me point out, so that we don't forget, right? You can always check, is this the right answer? Right? Is this the right answer? On an exam, you get this and you're asking yourself, is that right? So what's the derivative of that? Negative 1/2 outside. You've got an exponential. The derivative of that is the exponential times the derivative of the inside. The negative 1/2 and the negative 2 cancel, leaving you with x e to the negative x squared. Perfect. Exactly what you started out with. You know it's right. How are we doing? Consider this. Can we make, very nice, Arun? But for those who might not follow that, can we make a U-substitution to make the whole thing simpler? So Sophia is asking how we went from here to there. So you've got the x dx here, and that's exactly what you have in the original integral. So this x dx gets replaced with negative 1/2 du, and then you're just left with the exponential e to the negative x squared, but negative x squared is u, so this is really e to the u. Theta equals u, that's fine, but that's not going to make much of a difference, right? Because this theta is just a dummy variable anyways. So whether it's x or u or anything else, it's not going to make the integral any easier. Somebody's suggesting u equals sine theta, and let's see why that is good. What is du d theta? What is the derivative of sine theta? You know the derivative. You know it's cosine. So again, du is cos theta d theta. I'm going to stop now. I'm going to stop writing this intermediate step and just go from here to there. I think you can follow that. So du is cos theta d theta, and once you know it, cos theta d theta is exactly what you have here. So that this becomes, this cos theta d theta is du, and now you're just left with sine squared, but sine is u, so this is just u squared. Very simple integral. Now, some people are asking, why not cosine theta for u? If you take u as cosine, what's du? du is negative sine. No problem, you have one of these sines here, but then you'll be left with one sine. And your u was cosine, so it's going to be difficult to rewrite sine in terms of cosine, or to rewrite sine in terms of u. U equals sine makes a lot of sense because you see the derivative right there. U is x squared makes a lot of sense because you see the derivative right there to within a constant. And that's the idea. If you want to make a U substitution, you should essentially see its derivative in the integral. Trivial integral now. You know what the antiderivative is. 1/3 U cubed. And U was sine. There it is. You can verify by taking the derivative, and you'll see you get exactly back to this. Michael is asking if we're able to let U be sine 2x. I mean sine squared of x. What would the derivative be in that case? Du, the derivative, 2 sine theta cos theta d theta. So if you bring the 2 over there, you have a sine theta cos theta d theta. So one cos disappears, one sine disappears, but you'd be left with one sine. So you'd be left with the square root of U. That would work as well. Absolutely. Absolutely. I'll let you try it and convince yourself that you get exactly the same answer. But if you cannot directly put du in the function, then probably it's not the right U. Right. Let's look at this. You have options. You could expand this out. You could multiply this out 10 times. You understand what's going to happen, right? I mean, you'll get some big polynomial of degree 10. And then you could integrate term by term. So that's doable. But I'm sure you understand that that's going to be terribly long. Surely there must be a simpler way. There is, and as suggested, we'll go with a U substitution. U equals 5 minus 3x. If this was just U to the 10, this integral would be trivial. And that's exactly what's going to happen by making this U substitution. U equals 5 minus 3x. So that du is minus 3 dx. Right? The derivative times dx. Let's bring the minus 3 to the other side. So minus 1/3 du is dx. And this integral, dx, is minus 1/3 du. And this is u to the 10. Minus 3 dx, right? Don't forget the dx. Sophia is asking if we just find a u that makes the antiderivative trivial. I wouldn't go as far as saying trivial, but easier to find. How do you choose what U is? Exactly, right? I mean, that always comes up. It has already come up earlier in today's lecture, and the answer to that is experience. Experience. You need to do so many that you know what to do. One-third? Well, I mean, it's the antiderivative of U squared. We saw the formula, right? Antiderivative of x to the n is 1 over n plus 1, x to the n plus 1, when n is not -1. In fact, we saw that in calculus 1. Antiderivative of this, right? We'll take the -1/3 out. Antiderivative of u to the 10. Same formula here. 1 over 11, u to the 11. Or as somebody had suggested, -1 over 33. U is 5 minus 3x. So u to the 11 plus c. There you go. Where does the 1 over 11 come from? I mean, I've rubbed it off now, but it was that antiderivative of x to the n business. Here it's x to the 10. Antiderivative of x to the 10 is 1 over 11 x to the 11. Consider this. Can you pull the -1/3 in the integral out because it's a constant? Exactly. That's exactly what I'm doing, right? I'm taking it out. And I'm just looking at u to the 10, whose antiderivative is 1 over 11 u to the 11. Kevin is suggesting a U-substitution with u equals 1 over x. An excellent suggestion. If u is 1 over x, then what is du? If u is 1 over x, du is -1 over x squared dx. Don't forget the dx, right? -1 over x squared dx. And observe that 1 over x squared dx is exactly what you have. So if you bring the negative to the other side, then this 1 over x squared dx is a negative du. Rudy is asking what is dx, but go back. First of all, the real answer is that dx is something called a differential. We didn't discuss them in Cal 1. We're not going to discuss them really here either. If you want a comprehensive approach to that, The topic is known as differential geometry. No need for me to write that down. Differential geometry. You can take a course in differential geometry, and it'll explain exactly what this dx is. Some books, some calculus books, refer to them as infinitesimals. The idea is, right, I mean, in the Riemann sum, as n gets smaller and smaller, this Riemann sum, the sigma becomes an integral, f of x, and this delta xi becomes a dx. So that's what a dx is. It's these widths getting smaller and smaller and smaller, closer and closer to zero. Do we have to put the du at the end, or is that just convention? It's notation, but it's important notation in this situation here, right? The dx in terms of du is very important. The function is multiplied by dx, correct? So this 1 over x squared dx is negative du, and then you're left with the sine of 1 over x, which is sine u. Antiderivative is trivial. I'm sure you've done it already. Cosine u plus your arbitrary constant, or cosine 1 over x. Which again you can verify by taking the derivative. Derivative of cos is negative sine 1 over x times the derivative of the inside, which is negative 1 over x squared. The negatives cancel, and you're back there. Easy to see. Michael is suggesting a U-substitution where u is x plus 2. And that's an excellent suggestion. Let's see what happens here. If du is x plus 2, if u is x plus 2, then du is, the derivative of this is 1, so it's 1 dx. Du is dx. So this dx is du. Here, x plus 2 is u, so this becomes square root of u. Very nice. Very nice, right? But now we have an x outside, and we certainly don't want x's and u's in the same integral, right? And as was suggested, if u is x plus 2, then x is just u minus 2. So this x is u minus 2. And you see the issue we had before with the square root of x plus 2, which was problematic for us, this summation now is taken outside by making this U-substitution. Very nice. Very nice indeed. And now, the sum or difference being outside of the integral no longer poses an issue, because now we can distribute very easily, and this is u to the 3 over 2 minus 2u to the 1/2, and you can integrate term by term. Let's not think of it as making x u minus 2. The original U substitution was x plus 2. but then it turns out that we can solve for x. Integrate 2 over 5 u to the 5 over 2 minus 4 over 3 u to the 3 over 2 plus an arbitrary constant. Absolutely, thank you, Michael. And substitute back in. U is x plus 2. Minus 4 over 3 x plus 2 to the 3 over 2 plus your arbitrary constant. How did we get du as dx? Well, you tell me, right? I mean, you know, we skipped a step. What is the intermediate step here that you can do in your head? If u is x plus 2, what is du dx? Maggie? The derivative? Derivative of x plus 2 is 1. So now, in a terrible abuse of notation, think of bringing the dx to the other side, and we get du is 1 dx, or du is equal to dx. Matthew is suggesting a u-substitution here. U is 2 to the x. Nothing wrong with that. I think Yuan Ming may be giving us a slightly better one. With a plus 3, again, nothing wrong with Matthew's original suggestion. Both work. Why do I say terrible abuse of notation? Well, because this du dx is not a fraction, right? I mean, it's not du divided by dx. It's notation for the derivative. These things don't separate. But this du business and this dx business, these things live independently in another realm. And even though you're not allowed to do this, it actually does give you the right answer. We won't lose marks for this skipping this step, because, I mean, I've stopped writing it down, right? Nobody writes it down. Everybody goes from here to there. And so should you. How did u minus 2 go to u? Well, I mean, we didn't have u minus 2. We had u minus 2 times square root of u. So you know, you distribute and you get this, and then you integrate. If u is this, what is du? Michael is giving us the du. Du is 2 to the x log 2 dx. Thank you. And you see that you have a 2 to the x dx here. So if you bring the log 2 to the other side, right, this 2 to the x dx is exactly what you have. So what does the integral become? This 2 to the x dx is 1 over ln 2 du. And then we're left with 1 over 2 to the x plus 3, which is 1 over u. So 1 over ln 2 is just a constant. We'll take it outside. Antiderivative of 1 over u, you know what it is. Antiderivative of 1 over u is ln of absolute value of u. And u is 2 to the x plus 3. So that's 1 over ln 2. No need for absolute values because this is always positive. And there it is. Again, you can verify that this is correct, and let's do so. What's the derivative of 1 over ln 2, ln of 2x plus 3? Right, this is just a constant. We'll leave it outside. The derivative of ln is 1 over, so you get 1 over 2 to the x plus 3 times the derivative of the inside. What's the derivative of the inside? Derivative of 2 to the x is 2 to the x ln 2. Derivative of 3 is 0. The ln 2's cancel out, leaving you exactly what you started out with. How are we doing? Questions? This seems like a good place to end. You guys practice this U-substitution over the weekend. We'll take it from there next week. Thank you all for coming. You guys have a good weekend. And I will, one question for a limit. Go ahead, Michael. If you have a question for limit of Riemann sum. Are you writing down your question, Michael? So if you find the integrand to be square root of 1 minus x squared and was told to find the limit of the sum, do I just plug in the integration from 0 to 1? I mean, that depends very much on what the actual limit was to begin with. I suggested it can always be made to be 0, 1, but the integrand itself may be different. If this was your original question, say it was a minus. If this was the original question, which I suspect strongly that it was, or maybe you had a 1 over n outside, then the answer is yes. This is the integral from 0 to 1 of 1 minus x squared. Indeed. Which is easily seen to be pi over 4, right? But the reason that it is between 0 and 1 is because you recognize this as the lower sum, if you will, or the Riemann sum taking the right endpoints. Right? If you take the right endpoints, and so on, the height of your rectangle is going to be these, right? Because this is the square root of 1 minus x squared. So the height of your rectangle is going to be square root of 1 minus 1 over n squared times the width. And so on for the next one. 1 minus 2 over n squared times the width. And so on, which gives you exactly that. So there's no guesswork. It's because it works. That's the reason. But like I said, on Tuesday of next week, we'll prove why you can always take 0, 1. But again, you're not taking 0, 1 arbitrarily here, right? Yeah. I mean, you'll see. You'll see what I mean next week. All right. Let's end it here. I will see you guys next week. Thank you all for coming. So does it depend on what the value is with I? Let's take an example. What if you had 2i here? If you had 2i over n, then this would, I mean, if you consider this 2i over n here, right? This is 2 over n when I is 1, and then 4 over n, and then 6 over n, all the way to 2n over n. So this could actually be viewed as a regular partition on the interval 0 to 2, right? Where each piece is length 2 over n. So that's what's going on. See you Tuesday, Kate. Right, that's what's going on, and it's natural to view it as a regular partition on the interval 0 to 2. What I'm suggesting is it could be done on the interval 0 to 1 as well. So there are two ways to view it. Either you view it on the interval 0 to 2, or you view this this way, where this is still on the interval 0 to 1. Right? So here the function wouldn't be 1 minus x squared, but it would be 1 minus 2x squared. So the function can be adjusted to the interval 0, 1. That's really what's happening. I'm suggesting you can always take the interval 0, 1. And we'll prove that on Tuesday. How are we going to prove this? Maybe you want to try it over the weekend. Think about it. It's a U-substitution. A U-substitution proves that you can always take the interval 0, 1. Think about that, and we'll do it together on Tuesday. Very well. I'll see you guys then. Yeah, for those of you still here, first of all, practice the U-substitution, and then try to prove that Riemann sum argument can always be done on the interval 0, 1. You guys have a good weekend. We'll see that on Tuesday.